Now let's revisit the coin problem in a different way. The question is, how many ways are there to pay $10 using one, two, or $5 bills? And of course, I'm not going to give all the details again. It's quite the same problem, except we just have ones, twos, and fives, and we want to construct 10, not 50. So the generating function is uh, this multiplied by this multiplied by this. So this corresponds to the ones, this corresponds to the twos, this corresponds to the fives. Okay, so this expression here is 1 over 1 minus x, and this one 1 over 1 minus x squared, and this 1 over 1 minus x to the power 5. And of course, to find the coefficient of x to the power 10, again I applied a Taylor series expansion to this expression, and just looking at the coefficient of the term x to the power 10, I obtain the number of ways to construct $10 using ones, twos, and fives as 10. Now, I'm going to uh, change this question involving order. What if the order you give the bills is important? What if the order matters? Now, this is similar to the previous question. In this case, the generating function is x plus x to the power 2, x to the plus x to the power 5. This can be repeated 0 times. Now, this is the selection for the first bill. Here, I can select a $1 bill, or a $2 bill, or a $5 bill. Okay, and then this is the next selection. So um, I can make a selection 0 times, and 1 time, and 2 times. So this corresponds to the constructions using 0 bills in total. This corresponds to the selections with a single bill, either 1 or 2 or 5, and this corresponds to uh, the configurations with 2 bills. Okay, and addition up to infinity. Now this is an expression of the form y to 0 plus y to 1 plus y to 2, y to 3, etc. Y here, of course, corresponds to this term here, x plus x squared plus x to the power 5. But it's in the same uh, form, so this should be equal to 1 over 1 minus y, and just plug in y as x plus x squared plus x to the power 5. This is what you get. And this function, if you apply the Taylor series expansion and look at the coefficient of the term x to the power 10, you get 128. So when the order becomes important, you can form $10 using ones, twos, and fives in, instead of 10, now 128 different ways. So generating functions can also handle orders and without orders problems. Okay, so another typical problem is this distribution problems. How many ways are there to distribute 10 cookies to 3 children if each should get at least one? Okay, so again, this is a problem you can do without generating functions, but let's see how we can do using them. The generating function here is uh, now it starts from not 1 but x. Why? Because I'm disallowing the configuration where any of the children gets 0 cookies. So that is disallowed, and therefore the generating function starts from x to power 1, and then x to power 2, x to power 3, etc. And I take the third power here because I have 3 children, so each of their generating functions are multiplied. And when you expand this expression, I used again Wolfram alpha, and look at the coefficient of x to power 10, which is here. So the answer is 36. Now, there is a detail here. You see, x to power 10 means you allocate 10 cookies to one of these children, okay? And in your expression, you see x to power 30. This means there is one single way to allocate 30 cookies to 3 children by allocating 10 to each of them. And when in the scenario where you have just 10 cookies, of course, none of the children will have 10 if you disallow 0 cookies, right? Because even if you just give 1 to the first, 2 to the second, the third one will get at most 8. So I can actually truncate this from 8. Okay? So none can get 9 or 10. So the generating function can also be expressed in this way. But this leads to the exact same result because the coefficient of x to the power 10 is 36, which is not surprising because in the combination of 10, if you disallow zeros, you will not have, like, even if you have x from one and x from the other, you cannot get x to 10 from the third one. Okay, so it's unnecessary to use x to the power 10 in this case. However, you can also look at this from the other way around. Now, does it make my life easier to actually exclude them or include them? Because in either way, I get the same result. So if it is easier, maybe if you are doing it by hand on paper, maybe you would like to work with less number of terms, so then exclude them. But if you are if you are not really expanding the generating function, but looking for analytical solutions, instead of truncating it at x to the power 8, just continue this towards infinity, in which case you will have x plus x squared plus x cubed dot 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 to the power 3. Why would I do that? I know that most of the terms here are going to be irrelevant because I just need the term x to the power 10. However, if I write this in this way, then it becomes easier to represent this as a compact function, which is easier to manipulate, like in 1 over 1 minus x, similar to 1 over 1 minus x 4. And we will see examples of this.